Hi guys, welcome back to my channel. So in this video, I'm going to do an integral, which may look quite freaky and accordingly has a very interesting final answer. With that, let's get started. So the integral in question for this video is integral from 0 to infinity, sine of root x, natural log squared of 1 over root x divided by x dx. Okay, first of all, noticing that we don't like the roots, we can do the substitution x goes to x squared. I could always call it a different variable, say u equals x squared, do the substitution, or just do it in this way. In this way, it's a simple substitution. That's why I'm not gonna show the steps, and I'm gonna just write x goes to x squared, because we can always find what dx goes to, and accordingly. Now the upper and lower bounds remain the same, and that's essentially why I'm using the shorthand notation anyways. Okay, so we have this 2 times integral 0 to infinity sine of x, natural log squared of x divided by x dx. In between this substitution and this step, I would have gotten natural log squared of 1 over x, which I flipped using the properties of the natural log, getting two minus signs which cancel each other because of the square, and then in the end we end up with ln squared of x. So if we consider I of k, which is a general family, whenever you see a natural log and a polynomial in x, you might want to think of using this strategy of considering a general family and then differentiating, because if you differentiate an exponential function like this x to the k with respect to k, you're gonna get natural log. That's why considering this family of integrals is a very good strategy in this case. Integral from 0 to infinity sine of x over x to the k dx. Now notice that, and this is the point I was talking about, I prime of k is minus integral from 0 to infinity sine of x over x to the k ln x dx. So you get a minus from the exponential being in the denominator and the natural log. Now two derivatives and the minus disappears. Integral from 0 to infinity sine of x over x to the k ln squared of x dx. Now interesting thing is to know the relationship between the second derivative of the family and the original integral we had. So if we plug in k equals 1, so if we take the limit as k goes to 1 of I double prime of k, we're going to have x to the power 1, just like over here, but the I had an extra factor of 2. So I is 2 times limit as k goes to 1 of I double prime of k. Fair enough. So our strategy is going to be evaluating what I of k is and then differentiating it 2 times, taking the limit and then multiplying by 2. Now how do we evaluate it? Well, that's where this observation comes in. So if you look at integral from 0 to infinity e to the minus dx t to the k minus 1 dt, for those of you who are quite perceptive, you might notice this as a Laplace transform taking place in the t world and then going to the x world. It's a Laplace transform of a polynomial function, which happens to be a gamma of k over x to the k for polynomial raised to power k minus 1. If you don't see that, if it's not obvious, that's fine. We can always do a substitution, u equals dx, and when we do that, we end up with 1 over x to the k integral from 0 to infinity e to the minus u to the k minus 1, and you should recognize this integral as the gamma function or gamma of k. So in both cases, we whether you see it's a Laplace transform or you do the substitution, you're going to end up with gamma of k over x to the k. Why is this important? Because we can write 1 over x to the k as 1 over gamma of k times this integral from 0 to infinity of e to the minus dx t to the k minus 1 dt. Now, all we have to do is just substitute in place of 1 over x to the k in the original integral. You might ask, how is that going to help us? We're just introducing more complexities in the problem, and you'll see why. 1 over gamma of k e to the minus dx t to the k minus 1 sine of x dt dx, both going from 0 to infinity. Now we can interchange the order of integration. I'm not going to go into the mathematical nitty-gritty analysis details of this. All you have to know is, since there's an exponential, it's all well behaved because it eventually decays. So, we can easily do this kind of operation. 1 over gamma of k times integral 0 to infinity, 0 to infinity, e to the minus x t to the k minus 1 sine of x dx dt. So we changed the order. So the dx integration happens first. And we can do that because it's e to the minus xt times sine of x dx, which is precisely the Laplace transform of sine of x. Now you can prove that by doing the integration explicitly, that you actually get 1 over 1 plus t squared, which is the Laplace transform of sine of x from x to t. You can prove that by expanding the sign as an exponential, e to the ix minus e to the minus ix over 2i, and then individually doing those integrals and then simplifying it out. Or you can just look it up in a table of Laplace transforms to get that sine x goes to 1 over 1 plus t squared. And again, the t to the k minus 1 factor remains. But now we lost one integral. We are in the t integral from 0 to infinity of dt. So we see a square down there. We don't really like it that much. So what we can do is we can do the substitution. T squared goes to t. Again, this is an easy kind of u substitution. That's why I'm not writing u equals, u squared equals t or something like, or t squared equals u or something like that. It's pretty simple. You can pause the video and do it on a piece of paper. In fact, I highly encourage you so that you know exactly what's going on in this video. Okay, so I of k is 1 over 2 times gamma of k integral from 0 to infinity t to the k minus 2, k over 2 minus 1, I'm sorry, divided by 1 plus t dt. Now, and this is the important part, is we are going to do a u substitution, and this is a non-trivial substitution. That's why I'm going to do it. So u is t over 1 plus t, and therefore if we invert this, t equals u over 1 minus u. It's just a few lines of algebra to check this. Dt therefore is going to be, we can use the quotient rule on this to get du over 1 minus u the whole square. Now I of k is 1 over 2 gamma of k integral from 0 to 1 u to the k over 2 minus 1 over 1 minus u to the k over 2 minus 1, which results from the t term, the t term. And then we have the differential term, so du over 1 minus u squared, and then the denominator term, which is 1 plus t term, which just becomes 1 minus u in the numerator. One of these cancels with the one in the denominator, and we end up with u to the k over 2 minus 1 over 1 minus u to the k over 2, because one of the minus 1 exponent cancels with the factor in the denominator. So 1 over 2 times gamma of k is equal to integral from 0 to 1 u to the k over 2 minus 1 times 1 minus u to the negative k by 2. I'm just bringing this denominator in the numerator, so we get a negative power du. Now notice that this fits closely with the integral representation, one of the main integral representations of the beta function. So beta of a comma b is equal to integral from 0 to 1 u to the a minus 1 times 1 minus u raised to b minus 1 du, which also happens to be gamma of a times gamma of b divided by gamma of a plus b. So if we match the forms, we see that we have 1 over 2 times gamma of k times the beta of k over 2 comma 1 minus k over 2. Now we can use the beta to gamma relationship that I've written on the rightmost side of the yellow equation to get gamma of k over 2 times gamma of 1 minus k over 2, and then we have in the denominator gamma of k over 2 plus 1 minus k over 2, of course with the prefactor in the front of 1 over 2 times gamma of k. Now everything simplifies nicely because in the denominator we have k over 2 minus k over 2 gamma of 1. Gamma of 1 is 0 factorial, which is 1. So we have 1 over 2 times gamma of k times gamma of k over 2 times gamma of 1 minus k over 2. And this should feel familiar because we have a nice reflection formula for the gamma function. Gamma of z times gamma of 1 minus z equals pi over sine of pi z. Now, plugging everything in and simplifying it, we get 1 over 2 times gamma of k times pi over sine of pi k over 2, because the z was k over 2, matching the formula. Okay, fair enough. We've solved I of k. We know what the I of k integral amounts to. And I of k was, let's just go back and review. I of k is this family here, sine of x over x to the k dx, integral 0 to infinity. But we need this. We need to find the two derivatives of I of k, second derivative I of k, take the limit as k goes to 1 and then multiply by 2. So to do that, let's first take two derivatives. There's no, real shortcut about it. You could be a little smart and reduce the algebra by just, taking care of the sine or the cosine term that you need. But I did this when I was not recording the video. I just wrote everything down so that, people know what I'm doing and people don't question me when I skip steps, because it can be confusing. So I prime of k is actually going to be, now we can just use I've used the quotient rule here. Is either the quotient rule or the chain rule. So minus pi over 2 times gamma prime of k sine of pi k over 2 plus pi over 2 gamma of k times cosine pi k over 2, and then the entire denominator just gets squared. That's the first derivative. Now the second derivative is even more complicated, obviously. So for the second derivative, I'm going to actually use a product rule. So what I'm going to do is I'm going to look at the numerator times, I'm going to look at this I prime of k as the numerator times 1 over this factor, so which is gamma of k sine of pi k over 2 quantity squared. That helps me, get rid of those extra factors that might be lying around that you would get by using the quotient rule. So the product rule is a better strategy here. Regardless, you're going to get minus pi over 2, and then in bracket gamma double prime of k sine pi k over 2 plus pi over 2 gamma prime k cosine pi k over 2 plus pi over 2 gamma prime k cosine pi k over 2 minus pi squared over 4 gamma of k sine of pi k over 2. That entire thing divided by gamma of k sine of pi k over 2, whole thing squared. But that's just the first term. That was just differentiating the numerator as we would do in product rule. And then now we have to differentiate the other function. So pi over 2 times gamma prime sine pi k over 2 plus pi over 2 gamma k cosine pi k over 2. And we have this extra factor from the chain rule, gamma prime k sine pi k over 2 minus pi over 2 gamma k cosine pi k over 2. Entire thing divided by pi k, gamma k times sine pi k over 2. Now that was quite a mouthful to say. The main thing is we have to now take the limit. So when we take the limit, you will see that all the terms with the cosine in it will vanish, because cosine of pi k over 2 when k goes to 1 is cosine pi over 2, which is 0. So when we take the limit as k goes to 1, we just have to look at the terms with the sign in them, because the sign will go to 1 and also the gamma of 1 is 1. So it really simplifies down, because in the first term you see there's a sign, so that goes to 1. We have gamma double prime of 1, which I'm writing here. The cosine term vanishes, this cosine term vanishes. We have gamma of 1 times sine of pi over 2, which is just gamma of 1 with this negative pi squared over 4 prefactor. That's the first term. And then the second big term, the cosine vanishes here. So, and of course the denominator in the first term is 1. Let me say that before I forget. In the first term, we have gamma prime of 1. The second term added to it vanishes. The denominator is identically 1, so that's fine. Gamma prime of 1 and then sine of pi over 2, which is 1. And then this term we can ignore. So finally we get minus pi over 2 gamma double prime of 1 minus pi squared over 2 gamma of 1 plus pi times gamma prime of 1 times gamma prime of 1, which I can simplify as minus pi over 2 gamma double prime of 1 plus pi cubed over 8 gamma of 1 plus pi times gamma prime of 1 squared. Now we have to find the gamma of gamma of double prime of 1, gamma double prime of 1. So for that, let's go back to what we know about the derivatives of the gamma, also known as the digamma function, which isn't really a direct derivative of the gamma, it's the derivative of the natural log of gamma. So that's gamma prime of x divided by gamma of x. That's the digamma function, which is also known as the 0th order polygamma function. I'm going to use the 0th order polygamma notation for digamma because we're going to need higher order polygamma functions in this particular case. Because if we differentiate digamma or polygamma of order 0 once, we can use the quotient rule here to get gamma of x, gamma double prime of x minus gamma of x whole squared divided by gamma of x squared. And that is equal to, that's the definition of the polygamma of order 1 of x. So if you differentiate order 0, you get order 1, which is very nice. And now we see that polygamma order 1 of x, gamma of x squared equals gamma of x, gamma double prime of x minus gamma prime of x squared. So now let's just plug in 1. So we get polygamma order 1 of 1 equals gamma double prime of 1 minus gamma prime of 1 squared, because gamma of 1 is 1. So now we get the relationship before we proceed, we can actually substitute what gamma prime of 1 is. So gamma prime of 1 is by definition equal to gamma of x times the polygamma of order 0 of x. Gamma prime of 1, if we plug in 1, is polygamma order 0 of 1 and then times 1, which is basically 1. A gamma of 1 is 1. So now digamma of 1 or polygamma order 0 of 1 is actually negative Euler-Mascheroni constant. I have made a video on this. Please check it out. I've explicitly calculated it from the integral representation of the gamma function, and it's a very, very satisfying result. So we finally get the equation that gamma double prime of 1 is actually polygamma order 1 of 1 plus Euler-Mascheroni squared. Now we can find what the value of polygamma order 1 of 1 is. We know polygamma of order m of z is actually minus 1 to the m plus 1, m factorial, the Hurwitz zeta of m plus 1 comma z. The Hurwitz zeta can be written as this infinite power series, k equals 0 to infinity, 1 over z plus 1, z plus k, sorry, to the m plus 1 power. Okay, so what we need is we need m equals 1 and we need g equals 1. So when we do those substitutions, we have 1 factorial sum from k equals 0 to infinity, 1 over k plus 1 whole squared, which is just Riemann zeta of 2 because 1 factorial is also 1. And we get Riemann zeta of 2, we know is the famous Basel problem, is pi squared over 6. Also, before I move on, quick note about the formula here. This is this formula for the polygamma of order m of z is derived actually from the series representation of the digamma function, which is derives from the product representation of the gamma function. I've made, I think, 2-3 videos on it at least. Please check them out. Okay, now moving on. Now we actually know what gamma double prime of 1 is. It's actually polygamma order 1 of 1 plus Euler-Mascheroni squared, but we know what the polygamma order 1 of 1 is. Pi squared over 6 Riemann zeta of 2 plus Euler-Mascheroni squared. That's nice. Now we can just plug it in this formula that we had on top. So limit as k goes to 1 of I of k is just minus pi over 2 times pi squared over 6 plus Euler-Mascheroni squared plus pi cubed over 8 plus pi Euler-Mascheroni squared. We simplify, we get a negative pi cubed by 12 plus pi cubed by 8 plus pi gamma squared minus pi over 2 gamma squared, where gamma is the Euler-Mascheroni. And finally, we get pi cubed over 24 plus pi over 2 gamma squared. But let's not forget the prefactor 2 we need to multiply. I is 2 times the limit k goes to 1 of I of k. We just found the limit part in the yellow. So multiplying by 2 and writing the initial integral out, we get pi cubed over 12 plus pi Euler-Mascheroni squared. Isn't that such a fascinating result? We have pi cubes. We don't really get pi cubes. And then not to mention the pi times Euler-Mascheroni squared. Like, we've never had this. The closest we've ever got to multiplying these two transcendental constants was with the borderline divergence integral. I'm sure you remember it. It was quite a nasty problem to do directly. Not to mention the quick trick I had in the end using the inverse Laplace and the Laplace transform. But that's the closest we ever came to having two transcendental constants multiplied like this alongside each other. Hey, but this method that we had in this video, we can actually prove what the borderline divergence integral was. So this, whatever I did in this video with the gamma function, writing the 1 over x to the k as a gamma function integral, we can actually totally use that to prove the answer of the borderline divergence integral. Now, for those of you who don't know what the hell I was talking about, here's the integral, the borderline divergence integral, as it's called on my integrals playlist, is j equals integral 0 to infinity ln x sine x over x dx. Now, if you remember I of k was sine of x over x to the k dx integral 0 to infinity. We noticed that if we take the derivative of I of k, so I prime of k with the minus sign, and we take the limit as k goes to 1, we're actually going to get this j. Now, the good thing is we actually did all the calculation for I prime of k. So let's just use the result what we have and then take the limit and then multiply by a negative. So when we take the limit as k goes to 1, the cosine term, like before, drops out. And we have gamma prime of 1 sine of pi over 2, and then the denominator is also 1. So we have pi over 2 times gamma prime of 1. Gamma prime of 1 is a minus Euler-Mascheroni constant. So we have that right there. Also, I absorbed the minus that was in front of the pi over 2 with the minus that we have here. In case you're wondering where the minus disappeared, well, this minus absorbed the minus that was on top of the in front of the pi over 2 factor in the original I prime of k expression. And that's why we get pi over 2 times gamma prime of 1, which is negative Euler-Mascheroni times pi over 2, which is exactly the result we derived in both methods, the contour integration method, that was the brute force method, and the elegant method of, well, using the Laplace and inverse Laplace transforms. And now we have another method of evaluating this borderline divergence integral by the use of the gamma integral, the gamma function integral, and then just switching the integration around. And you can call it a glorified Feynman technique with a gamma integral in it. Anyways, I hope you liked this video, guys. I really found this result fascinating, especially the one with the ln squared sine of sine and ln squared. It's very rare, and again, it's going from 0 to infinity, so it's not really that trivial. Hope you liked this video. Please like, share, and subscribe to my channel, and in the meantime, peace out.